Okay, this is the last assigned project where it's something that I think is cool, important, nice demonstration of things that we've been talking about. And it's called a yo-yo de-spinning mechanism. Have you ever heard of this or seen how this works? It's typically for spacecraft kind of stuff. And here, let's do a quick Google search for our Spaceloft 7 launch. Skip over the ad. So anytime you're kind of launching a system or kind of applying thrust, there's got to be some torque created from the thrust. And even if it's really small, sooner or later it adds up and now you're spinning really fast because there's nothing to stop you from spinning. So that's kind of what we're going to see here, is just due to a small torque, this thing starts spinning. And one way to counteract that is that you have thrusters that are sort of stabilizing you. But now you're using up thrust to stop yourself from spinning when that could have just been forward momentum. So it's kind of a waste of real high value fuel. So instead, yo-yo de-spin is these little masses on a fishing line or something. It can be really cheap materials that you can mount to the side of the spacecraft. And what we'll see is that when they get deployed, it kind of looks like a small explosion. And the whole thing will stop spinning and even start spinning a little bit backwards in the opposite direction. So we'll all get a little sick and then deploy, and then it stops. And now it's even moving in the opposite direction too. And it's kind of amazing that this kind of thing even works, because all it is there's no computer controller, there's no monitoring. You don't need high-speed monitoring or anything, or expensive fuels. It's a string and a ball, and you release the ball, and as it moves away from you, your angular momentum is now transferred into that ball, and then then the rope releases, and now the ball has all your angular momentum, and you're not spinning anymore. At least if you're careful about it. If you're not, then you start spinning the opposite direction, which we just saw. So let's take a look. We'll do a tour of the project, at least in its initial state. And the goal here is designing our own custom yo-yo de-spinning mechanism. Years ago when I designed this, it was oh, there's a car in space, that'll be cool. There's nothing political or weird about that, and now it's very political and very weird. But anyway, here we are. Yeah. If it ever comes back, would we get a tariff on this car if we tried to bring it back? Maybe, because it's been over other countries at this point. Yeah, we might have to pay taxes on it, or tariffs. Sorry, are tariffs taxes? It's a different name. Different type of tax? I don't know. Anyway. But anyway, so here's our Tesla Roadster. It's all right, imagine that the fake person in here, or maybe we could put a real Elon Musk in there and let him drive off into space. But it's corkscrewing around the axis. So the person is spinning around that grill axis. So I made an approximation that a roadster is some kind of box. So I needed the mass of the roadster, I needed its width and its height. The length didn't actually matter. It doesn't actually factor into, it factors in if it's really long, then it's going to be heavier. But it's not directly part of the calculation of what is the moment of inertia of this car to do a corkscrew. And that's what I really needed. So I need its width, I need its height, and total mass. And then my moment of inertia here is this formula that I looked up in like lists of moments of inertia for cubes and solids, m over 12, w squared plus h squared. So these are kind of the setup variables for my payload of what I'm trying to despin. And then these other two things are the design variables for like how fast am I expecting to spin, so W0, and then also M of like how big my yo-yos are. I think initially I said 10 grams, but we were just playing around with it in the last. Oh, and then one other thing. R is the first radius of the yo-yos, like where they're gonna start. Really, I should say W over 2, like mount them to the sides of the doors, but anyway, they're at W, so they're weirdly mounted on these like giant side view mirrors or something. I don't know. So we'll run that. I'm gonna run the simulation, like look at results of the simulation from like 0 to 1 seconds, like 100 steps along the way. So then I get a cool plot of like spiral plots are always cool. And it's the path of the two yo-yos on either side of my car. To give you like orientation of what this graph is looking at, imagine you're the driver watching just the yo-yos. So that's what this graph is. So it's not factoring in the fact that you're spinning. It's as if the x-axis is a fixed reference of your eyes. When you release them, one yo-yo goes up, the other one goes down, and they keep spinning around your car until it looks like they start moving away on a straight line, kind of like that, at the ends of those two blue and red curves. So that one, it's cool, it's a pretty plot, but we need some numbers, right? Like, how do I build this thing? It's the main goal of like, what is this actually doing? So let's look at how fast I'm spinning, me in the payload, how fast am I spinning? And when is that number 0? Because that's my design parameter, because I want to stop spinning and I want to release the yo-yos at that point. So after about 0.6 seconds, I went from 15 radians per second, so I'm corkscrewing through space. I released the yo-yos. I didn't do any calculations, so I just have an unlimited length of cord that just keeps going on. So it goes from whatever, 0 out to 50 meters, however much it wants to take up. So it keeps moving further and further away until I stop spinning, and then I'm like, oh great, things worked perfectly. But then I didn't release the yo-yos, so now I start spinning in the opposite direction, which is a little weird. But now I'm spinning in the opposite direction. So ideally what I want to do is have my cord be that long so that when it reaches that length, it just lets go. It doesn't start coiling back in. Because if I try to coil it back in and use it again, I'm just going to start spinning, right? I'm going to undo all that nice work that I just did. So that's my design. So I need it to last for like 0.6 seconds at 15 radians per second. So let's see how long the cord needs to be. I need 17.1 meters of like fishing line for this 10-gram yo-yo, for these two 10-gram yo-yos. Seems good. So the question is, what if I'm spinning faster or slower? Do I need more? Let's say I'm spinning faster, do I need more cord? Does it have to be longer? With the yo-yos. Oh, should it be shorter? Yeah.
I'm saying if beta dot is faster, doesn't that mean that your cord is a shorter length?
Well, like if I take this number, this initial 15, and make it 100, like make it bigger, like do I need longer cords or shorter cords
In order to do what?
to get to this red dot. So the red dot is like my design variable of like, when I reach the red dot, I'm not spinning anymore. The system worked, and like disconnect it. Like I don't want it to do any more work to my payload.
I'm just curious about, because this is like a torque thing.
Yeah. Yep.
I mean, I know with like, at least with like rigid like bars and stuff, like torque increases with how far you are from the. I don't know. I can't think of the term right now, but you know.
As your moment arm increases, you have more torque.
Yeah, but I don't know if that would apply to like strength. I mean,
For
maybe.
string, yeah, this one's kind of weird because the string isn't directly creating a moment, but it is creating moment, right? Here, let's grab this guy. Copy this. So if I just look at like take a free body diagram of just my payload,
Yeah.
then initially I have tension and tension as those yo-yos start to move out, and then later on tension and tension. But the length of the cord isn't a moment arm because it's just where it's connected to my payload.
That makes sense.
Yeah. But if I connected it right to the center of my payload, one, there's no centrifugal force, so it wouldn't actually move away. And then two, there wouldn't be a way for it to like slow down from the point that you were saying of like, look, it's creating torque. I have tension somehow, and the tension is creating torque. So I need some moment arm there. You know. Cool. Yeah.
Are we like accounting for the mass of ball scans? Like, or is that in
let's go back. Yeah. Sorry, as I go back up and down. Right now, the mass is 10 grams, so everything's in like kilograms and radians in this case.
now,
Yeah.
instead of like changing the length, we just adjust the mass?
Yeah, we could. So if 17 meters is too big, like, all right, that's no good. Like, I don't have room for 17 meters of cord. Increase the mass, and now think about like, how much angular momentum a golf ball has on a string versus a bowling ball on a string. Same speed, same distance. Bowling ball has a lot more momentum than golf ball. Yeah, so mass is one thing we can play with. Yeah.
Does the radius of like the balls on the end of the string matter? Like how big they are?
So what's happening is they both start off at the same rate. So whatever that capital R is, here, let's copy this. So they're both starting off at R. So whatever distance you say R is, that's where the yo-yos are going to start off. But then at any point in time, if I look at, that's going to be like RP of T at that point. Like it keeps getting further away.
I meant more like the radius of like the ball themselves.
Oh, the ball itself?
Yeah.
For the most part, it'll have a small effect, but it gets smaller and smaller the further it is away. Yeah, let's do this. Do you know what the parallel axis theorem is? Have you heard of that? Yeah? What is it? What's parallel axis theorem? How do I write it down for moments of inertia? Oh no.
The moment of inertia of the first object
Yep.
plus like mr squared.
Yeah. Okay. So let's say that's my little mass, and it's attached to this cord. And that's my r, like distance to that little mass. So the moment of inertia around, let's call it G, like the center of mass of the whole center of gravity for the whole system. So IG is going to be, if it's a sphere, it's like 2/5 mr squared, something like that. 2/5 m, and I want to use a different d/2. We'll call that little d. So it'd be like 2/5 m times d/2 squared plus mr squared. So two things are kind of taking away the moment of inertia of the actual, like the shape of our object. One is that r is getting big pretty fast, like 17 meters is pretty big compared to a 10-gram item. Like its radius can only be so big. So for the most part, it becomes a point mass pretty quickly because r is so much bigger than d. So if r is much bigger than d, then it becomes mr squared. Yeah.
So you would want a longer string, because that means it would be like the maximum distance it can be from, you know, the shuttle is greater, so your mr squared would be.
Well, in terms of like how long you want that cord, in the video that we watched, it was probably short, like 1 meter, like 3-foot long things, and they probably had 50 of them, and you release one at a time until you stop spinning. And that's another way of designing. We're just thinking about like the case where you just want to design 2 of them, release them so you have, like, it'll stop you from spinning. So, and that D, even if it was like a centimeter, even if you're 1 meter away, R is much bigger than centimeter. Yeah. So yeah, as things move farther away from what they're rotating around, they quickly become a point mass, and it's a good assumption. Yeah. Okay, so there's this question. If I spin faster, what's going to happen to these 2 numbers? So right now we're doing like 15 radians per second, and then we come down to 0. What if I'm doing 100 radians per second? If this axis goes up, if I increase that value, what do you think? We don't have to be right. We're just going to test it. It's just, what's going to happen to time if we're spinning faster to that release time? If we spin much faster. Who says it'll take longer if we're spinning faster? Take longer, so we got 1. Maybe take longer. So 0.6 might become 1, make it bigger.
No, I think because
You think down?
they're going to be accelerating that much faster. So
Okay, so maybe
have a
there's
faster
like, they
movement.
already have a lot of speed, so they're gonna move faster. Also good. So who says they're gonna move faster, so time is gonna go down? Couple. All right, more. Or who says time is irrelevant and it's just a cog, you're all just cogs in the machine and we can't actually measure time? Or the time will stay the same? No. Okay. What about chord length? Who says we're going to have a longer chord because we're moving faster? Like our design length, how long it should be. We need more chord. Nobody. Who says we need less chord? Things are moving faster, so it's going to happen faster. Shorter chord. Maybe? Maybe one. The goal is guess and get it wrong so that it'll stick with you forever. You remember things that you get wrong. You forget things that you already knew. Who says there's going to be no change? That the chord length doesn't matter. It doesn't matter how fast you're spinning. Things will happen faster or slower, but chord length will remain the same. Maybe a couple. All right, how fast do we want to go? 100 radians per second or different value? Not all at once, just one number at a time, please. 100. 100's fine. So it's faster now. Everything's going to happen faster. And because everything's moving faster, I'm going to put an extra 0 in how many time steps I want, just so I get more data points in my path curve. So in terms of the path, I don't see a huge difference. I mean, I increased the number of data points that I had, but things don't look very different, at least to start. Now I see, before I was somewhere out here, that red dot, the red dot moved a lot closer to 0, which means that by design, this thing, if I'm spinning faster, things happen faster. Roughly, that kind of makes sense, right? Like, because if I'm spinning at 150 radians, or sorry, if I'm spinning 100 radians per second, my yo-yos were also spinning 100 radians per second. So as I release them, now they're spinning around me 100 radians per second. So the whole thing will happen faster. Now it's the big reveal. 0.6, 17.1, that was our previous 15 radians per second design. Now it's 0.1 seconds, so like 6 times faster, but exactly the same chord length. Everything happens, it'll get the same distance away to stop me from spinning, and that's it. It's kind of nice when things work that way. So that's so the main design, it doesn't really matter how fast we were spinning. If we have the mass of the yo-yos and our moment of inertia correct, then we'll be able to stop this thing from spinning no matter how fast or slow. It'll work either way. This is like, as far as like space design, this would be like one of those transition designs of like, we were approaching Mars and now we want to like now we want to start the descent into Mars. You can't do that if you're like corkscrewing your way in, because all the ways that you're tracking your position would be all screwy. So you de-spin, it's like, okay, now we're ready to start the descent. Or anything, same thing for that like shuttle. Maybe you take off, you want to fly as fast as you can straight up, but now you want to start tracking your position, de-spin, now start the rest of your like slingshot and like get your thing up into space. Cool. All right, so what I want to do today is you can pick your own payload and build, because the main things that affect it are like moment of inertia and where it's mounted. So what is R, what is the moment of inertia, and then how big are those yo-yos. So that's what we want to pick out today, is like what is the mass and what is the moment of inertia of your own payload. It can be anything. So I've seen things like somebody imagining launching their little brother into space, like giving them the appropriate spacesuit, versus like a cow. Somebody wanted to see, like, if you're de-spinning a cow that's corkscrewing through space, how big do the yo-yos need to be, how long of a cord. The payload can be whatever we want to send into space, since it's our design. We can design whatever we want. And then the extremes are kind of like the Death Star. Like, what does it take to de-spin the Death Star? That one you can get pretty deep into, like, moments of inertia, because Wikipedia has a lot of information about, like, actual engineering information about the Death Star. Or, yeah, so whatever we want to do. That's the plan. Pick a payload, yeah.
Are we only editing this setup over here to wherever we want our things to be?
Yeah, this will be the main, like, kind of design. Like, this is changing the main part. Sorry, I'm gonna scroll down to the bottom. In terms of, like, as an engineer, what do I need to deliver to, like, the people to get this thing to work? It's these two numbers of, like, how fast does this thing work, and when I design it, how long is it? So those inputs that we put at the top, those are the main things that affect these two numbers. Yeah. Then there's other stuff like the only other thing is, like, in here, if there's not enough time points, then sometimes the graph, like, the graph is not very impressive, just like 2 dots, because I just need to add more time to the simulation. So I can come back up here and say, bigger is better, give me 10,000 data points. And then I have lots and lots of, like, now I'm looking at what is the position every tenth of a millisecond, if I have 10,000 data points that way. Or you might need to extend time. Like, if you're de-spinning the Death Star, you're probably going to need to look at, like, 10 minutes worth of, like, maybe not 10 minutes, but, like, at least 60 seconds of, like, getting these things away from your Death Star. But yeah, just depends on where you're at.
Do we need to change, like, the equation for a moment of inertia depending on the algorithm?
Yeah, exactly. So this moment of inertia, this is like a box, and it's one specific axis of a solid box. So you might need to change, like, depending on what you're looking at, you can, we can either look it up or kind of calculate it another way. Or maybe we'll need to, like, take one and subtract another, something like that. Or sum up a whole bunch of, like, point masses. That's another way to do it. A bunch of little MR squareds. I like this one from Wikipedia of the lists of moments of inertia. It usually has at least a good starting point for what I'm looking for. What are you thinking about for thinking? Okay. Oh yeah. So right now we're only going to, like, 1 second. So go back up to that part where this part? Yeah, so to, like, and then that should
I'm doing it by yourself.
Okay, nice. Yes.
Oh, there we go.
Yeah, if you change that one to, like, 2. If you're having trouble, like, seeing the end of your curve.
And then this is just tells me what.
Yeah, yeah.
Okay.
So right now, are your masses still like kilograms?
No, I changed it to 100.
Oh, 100 kilograms? Okay, yeah, yeah.
I thought staples were 165.
Oh, so right now you're saying that it's
If it's spinning,
top end of brand.
no. I was doing it like if you shot it straight up, it should be like
But then why is the height part the number?
well, I just didn't like switch it. Like I made the thing 300 changes or 300 meters like tall.
Yeah.
And like I had to make the height dashboard. I made it like 10 wide.
Yeah,
So
so
if you're like looking at top bottom, it's like
so then the
because I didn't know how to like.
oh, I see. So length. You're saying length is tall. Okay, all right. Never mind then. So yeah, it's quarter string around.
Yeah.
Yeah, yeah. All right. Still pretty big.
It's like this mechanism is supposed to support
Yeah.
what the yogas are doing and stuff.
Yeah.
I'm not really sure like what, like how these all, like how all the dots.
Yeah, how it's all connected.
Like how, yeah, that's like actually yogas, I'm just saying yogas, or this is at X, Y, that's when you can circulate.
Yeah. But that one's like X, Y, like 0X, 0Y is the driver.
Okay, so this is the, like the car.
Yeah, exactly.
And so the car is like, always gonna be something else. And
Yeah.
depending on what that is, these patterns can be different.
It'll be a little different. They're always gonna look like that, like some kind of spiral. So for the most part,
So this,
they're unraveling and they're moving at a constant theta dot.
so the car, it's spinning. With the yogas, like spinning around.
Yeah.
And these yogas are gonna slow it down.
Yep. Yeah, so the car will slow down spinning, but the yo-yos will continue to spin.
Yeah.
Through a string. So the string can apply tension, but it can't apply torque. At least on the yo-yo. The yo-yo won't have any torque applied to it. So if there's no torque, then the theta dot is constant. That one, see how the angular velocity is 0?
Yes.
So
That's
that's,
far of the payload. And so once that happens, then they release the, the other set, so that the payload stops spinning.
exactly.
And
Yep.
this payload does keep spinning because there's momentum.
That one, if they keep, so like right now, we have that number, 17.15 meters at the bottom. Yeah, so if we design a yo-yo that releases at 17.15 meters, then we're gonna stop spinning, and right now we're not spinning anymore. But if we increase the length of the cord, like maybe 20 meters, now we're gonna be spinning backwards at 5 radians. We're spinning this way, now we're spinning this way.
It's like right hacking it.
Yeah.
Say it's like this way, right? And this is the point where this is 0, right? But then it gets released, so then it starts spinning.
If you don't release the yo-yo.
That's
That's just showing how,
this is if you don't.
yeah, that's showing how the system acts. Like, you have the yo-yos, you keep the cord attached and you let them just keep unraveling further and further away.
Yeah, I was trying to understand how the yogas stop it from spinning. So I guess is the payload, is that what starts spinning based on the yoga?
Yeah, so initially everything is like a rigid body, like everything's connected, nothing's moving.
And then the payload is given an initial angular velocity. And this is like state 1, and this is like state 2.
It's moving, that's the opposite, so like
This is state 1.
gray is state 1, or lighter, right? History to present.
that is the next place.
Yep.
And then see how that affects other tools, like graphs, and then try to answer the question.
Yeah, exactly. It's a lot, but I mean, a building in space is a lot. Yeah.
Do you think
It's about like 2 trucks. Use these things.
pretty much?
Yeah. I mean, it's not crazy. At least in the scale of like launching the Empire State Building into space. It's not undoable. It's not impossible. Because if you can get that into space, you can probably send a couple extra parts with it. Yeah.
Okay, so the payload starts spinning, and this is first like the all one thing. Payload starts spinning.
Yep.
The yo-yo starts to unmask because the yo-yo's getting these masses and then bouncing. But the momentum is translated from here to these masses.
Yep.
Okay. Yeah, but yeah, I just have trouble listening like happening in real time.
Yeah. Yeah.
Is the so I can hear bigger one. I mean, I'll try to present it. Yeah. Would be okay. Starship.
Yeah.
Okay.
You know, the yo-yo,
Yeah.
yo-yo type of mechanism. Then you just, stabilize this and then regain consciousness or something.
I tried this pot, but I just like added a toast on top of that. It's just really good. So, yeah,
Yeah, that one would include the payload, but also would include like all the thrusters.
yeah.
It depends on when you're using it, right? Yeah, I'll probably lose a few of them. Because I think at first, even if you're spinning a lot, you don't really care. You're just trying to get as much stuff as possible.
Watch the sun. Watch the sun. That's the other.
Pyramid?
Yeah.
Okay. Yeah.
6 billion. Still
Billion? That's a lot.
Yeah.
Yeah, that one. I forget what it's been, but it's a lookup value. Right?
Yeah.
Yeah.
You changed this one to say that last one.
Was 69.5 kilograms short for 48 meters. Like a real
What do they, how do they fry it?
It's because like when they catch it, eat it, it's spinning, but you don't release it. When they come back, when they come back, it's just gonna rocket's gonna take that momentum. And it's kind of like going back and forth, just for the sake of it.
Yeah.
I'm not sure if rocket substance like that, like just stopped.
Yeah, so see how your release is like 2 to 3 seconds? It's fine. There's that time that you're playing with, at least that I was playing with, little
Kilograms.
no, I wait for it to like T is in space. So if you change that, yeah. Oh, the big like beer. Yeah, nice. Yeah, yeah. What did you say? Like, does it have one? Sure. I mean, it has like.
No, it's not, but it's estimated like.
Yeah.
It's like above.
Yeah.
It's a solid cube.
No. Is it solid?
Yeah. And it never shows up. Just to see it.
Yeah. Yeah.
It might be decent also where,
Yeah. And that's like stretch up in philosophy. Yeah, I keep getting different cars. I do the Ford Raptor. Yeah. First day, I got a C. I think it's I just actually the length with. I got an A on the writing.
Don't have bunch of them.
What is my
We can never go to discussion.
When did that? Is they only actually just recalculated? Yeah. Like, would they kind of just have it the same result?
Like, what's the
Solid.
If you're using like just geometric shapes for your estimates, but solid objects that has the shape, you lose like some, you're probably losing certain things like, so two objects that have the same direction.
Yeah.
Like with a tight key, probably within 30%, there's a change from so dynamically there's a different but if we're really doing this, like this is kind of the first step, like can we build this system? The next step is, okay, let's build a CAD model, the thing that's actually going to space and tell the CAD program to give us a moment. Now we redesign it, but with the new.
If I choose it one thing or another, it's like these dimensions.
Yeah, and sometimes they're like two very different shapes. Dynamic, like the dynamics of them are exactly the same, just because they have the same like distribution. Yeah. So you could change it. I think even for that Tesla, you're using 10 grand. You know, something's not. It really isn't. You could try to do one, like, use the test or something. Yeah, which is roughly seen. Yeah, that's cool. The cord length is describing the yo-yos. In order for them to de-spin like 4 sats per 8, that's how long the cord needs to be. So in this case, like you might have an example. You launch and then you release a satellite, and you know you're not going to release it perfectly still. Maybe it is spinning, but it releases, right? So it has like a time delay for that yo-yo spin to like stop it and how not spinning. Yeah, so the cord length is like as it unravels around from the satellite out into space and gets to space 0.9, so almost 1 meter, and then releases and kind of disappears. Okay, so why ME6? Isn't Q also because I think you just have a dice. I think it's still W squared or H squared plus unless you're saying H squared, yeah, I think you would just delete that W squared. That makes sense. Yeah.
Sorry, just mass and stuff of giant rocks. Anyway,
Okay.
yeah, well, I was going to do this, but the mass doesn't, it's just weird, so I'm gonna something else. Anyways, I was just gonna ask about this stuff. If I were to be modeling like a humanoid, would it be okay to use like a cylinder? Or do you think it would be better to use something else, like a sphere?
Sphere usually works pretty well, and then ellipsoids work pretty well, because they're like for some reason like biological. I mean, it makes sense, but biological systems usually they're trying to maximize surface area at volume, which is usually either a sphere or an ellipse.
Okay, so which, I mean, I guess.
Yeah, it depends on what axis you're spinning, right?
Which is probably,
So like, yeah. So if you're spinning along the y-axis, that would mean that A and C are moving in a circle. Alright, if you're spinning along the z-axis, B and C are moving in a circle.
if we're not like going up, it would be the D, and then it would be A squared.
Like if you think of Superman, yeah, like flying, if he's corkscrewing, then I would think like that's his chest, his back, and then spinning along his y-axis. Versus like he gets hit in the face, and now he's like zero to the air. It's going around.
That'd be mass in one side,
Yeah.
and the ship, and then
Yeah, so it'd be like how wide
is that
like how big of a belly does monster have versus how wide like or the shoulder width of the monster.
but then you just let go. It's just gonna start from
You're also like stop the screen.
that makes sense.
I know we are.
Yeah.
We'll go.